Welcome to this video, and in this video we're going to be going over the searching and sorting algorithms for your GCSEs. Having said that, let's dive straight into the first search that everyone should know, which is called linear search. So how does linear search work? Basically, as the name suggests, so it searches for an item linearly. So each element in the list gets searched. So if we have an example array, let's call it x, and we let that equal to, and we want to find the value 2, what this algorithm would do is that it would start at position 1 and see, is that the value? No. So then we move by right, move a position to the right. Is 10 2? No. Is 2 2? Yes, it is, and it would return true or return the value. That's basically how the algorithm works generically. Now let's look at the code. Also, all these examples are going to be written in pseudocode, OC or exam reference language. So here's the code for linear search, and basically it's written as a function, and it takes two parameters: an array, which we're going to be looking at, so maybe it's x, and a value, which we could use any value. So we start the index off at 0, that's the beginning, and then while the index is less than array length minus 1. The reason why we minus 1 again, the length actually returns the number. So 1, 2, 3, 4, 5. 5 elements in this array. This would return 5. But we need an index, remember? Arrays start from 0 and go to n minus 1. That's why we have to minus 1, so that it's referring to this position here, which is at index 4. Which is the length minus 1. Then we have a condition: if the array at index position, so index is 0, if the first item is equal to the value, then we're going to return true. And because we're returning something, automatically stops the search in this while loop, and it just exits out the function. So what if the value is not found? Then we don't do this part, and instead we go straight to line 7, which is increase the index by 1. The reason why we have to do this is because it's not a count controlled loop, it's a condition controlled loop. Because we don't know the amount of iterations needed, we need to use a counter that adjusts inside the body of the loop. So once we iterate, then it's going to check the next value is 10, and it does that, so on. So if instead of v we had maybe 100, which is clearly not in this list, we would have to go through this list around 4 times so that we can see that it's definitely not here. So in general, this is a very inefficient algorithm because again, you're going to be searching through every item in the list. So imagine a list with 1,000 elements or maybe 1,000,000 elements, and that item that you're looking for is not even there. So it's going to be going through the algorithm 1,000,000 times. So yeah, hopefully you can see how this is an inefficient algorithm. And let's move on to a more efficient algorithm, which is the binary search. Also, by the way, I forgot to mention that you can find all of these booklets in the website. I'll be shortly uploading them, and you can see the pseudocode as well as the description, as well as comparisons between the searches and the sorts. So yeah, hopefully that is useful. And let's move on to binary search. So what binary search is basically we start off with the middle of the array or the list, and we compare it to the value that we're trying to find. If it's equal to it, we do nothing and it's found. If the middle value is less than the value we're trying to find, we're going to ignore everything to its left, because we know that everything to the left is going to be smaller than the value, including the middle value. So everything to the left we remove, and we just focus on the right. Then we do the same thing on the right. We find the middle value on the right sublist, and then we just keep doing until we find the value. And if we don't find the value, we just return false. Also, a prerequisite of this algorithm is that it must be sorted. So you can't do this on any array. For example, with a linear search, you can do this with anything, any array. However, with binary search, you do need a sorted list. Make sure you remember that. Let's have an example array again. So imagine we have x, and we have, this time it has to be sorted. So let me write that. It has to be sorted. So if we have x equal to maybe, and also if it's an even array, to find the middle one, we just use the middle's left one, like the left most. that's close to the middle. So in this example, imagine we want to find 12, right? It's right at the end. So let's see how we can do this. Firstly, as I said, we compare the middle value with the value that we're trying to find, and clearly it's less than the value. So as I said, you remove everything to the left of it. Now we only have 11 and 12 in the sublist. We're not creating a new list, we're just using the same list. Then what we do is that we find the middle, and this is an even number. So like what I said, you use the left one. So you use 11, and 11 is clearly not 12, and it's less than it. So we ignore this, and now we found 12, and 12 is equal to 12. Perfect. As you can see, that's already much more quicker. How many steps did that take? Maybe 3. And if you did the same thing with linear search, it would have taken you 1, 2, 3, 4, 5 attempts, because it's going to be checking all of them. So you can already see how powerful this algorithm is. However, it does need to be sorted, which is a downside of it. So make sure you know the pros and cons. Again, this will be all in the PDF on my website. You can go check it out. Okay, so this is how you do it, like for a human. So an algorithm, like the computer, won't know how to find the middle, how to like do things with an array. So we're gonna have to be more precise and more efficient in it with the code. So here's the code for binary search, and basically how it works is that basically we have 3 pointers: start, mid, and end. What the start pointer is, basically it points to the first element. The end pointer points to the end index. Remember, all of these are index positions. And the mid pointer does start plus end divided by 2. So it gets the leftmost value if it's an even number. Now that all our pointers are shown, again, the reason why we use pointers is because we can select and move them and show a certain part of the array without creating a new array. If the value at the midpoint, in this case 10, is less than the value, what do we want to do? We want to adjust the start pointer. So instead of pointing to the start, we point it to midpoint plus 1. So our new start pointer becomes over here, just like how we did in the example. This is at position 3 because it's 2 plus 1, which is 3. Then if now it goes back to the start, and midpoint equals start plus end divided by 2. So 3 plus 7 divided by 2. Not div, but div is the quotient, which is the whole number when you divide it. So we get 3, and clearly 11 is still less than the value. So since that's the case, we adjust S so that it's pointing to, again, this is mid, and S now becomes the end. And when we do this part, we get 4, and if it's less than the value, which it isn't, if it's greater than the value, which it isn't, in this case it is equal to it. So we just return true, and we exit out of the function, or the while loop as well. Yeah, don't worry if you don't get the code too much, but as long as you understand that we use 3 pointers, start, end, and middle, and how they move depending on like the value of the middle value, that should be all that you need to know. You would never be asked to replicate this in an exam unless you're doing maybe A-level or something. And we're going to now move on to the sorting algorithms. Now we come on to the sorting algorithms, and the first one is bubble sort. Everyone should know bubble sort. It's a very popular sorting algorithm which basically compares each pair and swaps it accordingly. It compares adjacent pairs, so the pairs that are next to each other, and if it's greater than, we swap it. So let's do an example as per usual. Let's have an array called X. So again, we use pairs and we compare 10 and 2, and clearly they need swapping. So we have 2 and 10, and the rest elements stay the same. Now we're going to be pairing 10 and 5, and clearly they need swapping. 2, 10, 5. They need swapping, so 5, and then we select 10 and 1. And we have, as you can see, after the first pass, the highest number bubbles towards the end, hence the name bubble sort. That's a quick mark that you can achieve just by looking at the name. Now on the second pass, we're going to be comparing 2 and 5. Clearly they don't need swapping. Then we're going to be comparing 5 and 1, which they do need swapping. So we're going to have 1, 5, and 10. Then we're going to have 5 and 10, which is going to stay the same. And that's second pass. Then we're going to be comparing 2 and 1, and that's going to be 1 and 2, then 5 and 10, which is going to be the end of third pass. And it double checks it one more time. That's very key. And once it does that, on the fourth pass, it's going to be all sorted. And hopefully that makes sense and everyone should know how to do this. Now let's look at the code. It's going to be very similar, having 2 pointers and swapping them. So let's see how it works in practice. So here's the code. Here's the code for bubble sort. And straight away, we basically have an array that gets passed in. We have a flag, which is this, which we set to false because we assume that the array is not sorted. So we set a flag and then we start the while loop while the flag is false. Then we temporarily set it to true because we're going to assume that it's going to sort it and see if there's any swaps being made. This also, it can be named like swaps. So it keeps a flag whether it swaps or not. Then we enter a for loop which goes from 0, which is the start, to array length minus 2 this time. Why is it minus 2? Because we don't want to go towards the end of the array. Remember, because we have this over here, it compares I with the one next to it. So I with I plus 1. The reason why it's minus 2 so that we don't go towards the end of the array. Then this part takes care of the swapping. So we create a temporary variable which temporarily stores the value at the first value. Then the first value gets assigned the one next to it, and the one next to it gets assigned temp. Then we let sorted equal to false because the array is unsorted or there has been the swap being made. Then we basically repeat until each element is sorted. So key points of this algorithm is that it uses a flag to keep track of either when it's sorted or not, or if a swap has been made depending on the pseudocode. And another point is that it starts from 0 to minus 2, so it doesn't go like out of bounds of the array. This part is key. This is like a three-way swap. Maybe you might be asked, what's the point of a temporary variable? Well, we can say that it stores the value that is going to be swapped or something along those lines. And yeah, these are the three main points of a bubble sort. It is very inefficient because even if this thing is sorted, even if the list is sorted, it's still going to run to check if it's sorted or not. Also, if you have a million items, you're going to be swapping a lot of things. So yeah, it's not very efficient. Now we're going to be talking about insertion sort. So how does this work? Well, basically, if we have an example array, again, as per usual, it sets the first item as like a sorted array or a sorted part. So we have 10 in the first one, which is sorted, and the rest of the elements are unsorted. By the way, it's the same array, not a different array. So now we take elements here and we insert it on the ones that's previous to it. So in like reverse order. So we get 1 and then 10. So it's important to know that this gets compared with every single thing that's previous to it. So it's like a bubble sort, but in the other way. Not really a bubble sort, but like if you get what I'm trying to say. So then we have 2 and 5. Then we compare 2 and we compare it with 10. And clearly they need to swap, so they swap. And that it goes in the correct position. So then we have 1 and 2. Then 10, and then 5 at the end. Then we basically check 5 with the rest of the elements. Then we're going to have 1, 2, 5, and then 10. That's how basically insertion sort works. Now let's dive into the code. So here's the code for insertion sorts. And basically what happens here is we take an array as per usual. But in this case, we start with the first element, so the second element in the array. And we compare it and we set j equal to I so that we don't accidentally change I, because I goes through 1 to the end. And the reason why we're minusing 1, we don't want to go past the end of the array. And then we have a while loop, which is checking that j is positive and we're not going more than left that we need to. The item that we're on is less than the one previous to it. If that's the case, then we're going to be swapping the one that's left to it. And again, you should all be familiar with how to swap it. It's similar to how you swap in bubble sort, but instead of the plus, we get a minus because we're comparing the one to the left of it. Then we decrement j by 1 because we're comparing each item to the one that's left to it. Once this is done, this part, then we basically move on to the next item. So if we have this example again, how this would look like is we have this array, then we start at position 1, which is this position, and while j is greater than 0, which it is because j is going to be 1, and the position at 1 is less than the position at 10. That's true, so we're going to set temp equal to j, which is 1, and j equal to the one that's previous to it, and the one that's previous to it is going to get set to 1. So then we have this going here, which is going to be, then we're going to decrement j by 1. Again, I is still here, but j is going to be at 1. It's going to be 0, and 0 is not greater than 0. So therefore, we get out of this and we go back to I. Then I is going to increase by 1 and go to 2. Then we're going to do the same thing. While j is greater than 0, which it is, and the one previous to it is less than it, which it is, we're going to swap these two around and we're going to get 1 and 2. And then 10 and 5. Again, I stays the same, which is here. And we're going to have j, which is j minus 1. So we're going to have j, which is here. And j is going to be at 1, which is greater than thing. But it doesn't satisfy this part over here. So therefore, we exit the while loop again. And we automatically increments I. So I becomes over here, and then we start again and we go into while j is greater than 0, which it is because j is going to be over here at first, and then we're gonna, and you kind of get the point. So it basically I don't know how to say it, but it basically checks all the ones previous to it and swaps accordingly. This is what this does. This swaps, basically compares the item that you're on with all the one that's to the left of it and changes accordingly. And this one is made for the individual element. So it goes through each element, and this one goes backwards. This is reverse. Again, the PDF will have everything in detail. So yeah, hopefully this makes sense, and yeah, now let's move on to the next one. So let's move on to merge sort, and in merge sort, as the name suggests, basically each element is divided into one list, an item of one list, and then we combine them back together. So this uses like a divide and conquer strategy. So first the elements are divided and then they're conquered, so meaning they're put back together. So again, let's have an example. 2, 1, 10 and 5, and what we do is just divide by 2 until they're separate. So we get 2 and 1 and 10 and 5. Then we get 2, 1, 10 and 5. Then we put it back together in order. So 1 goes before 2 and 5 goes before 10. And finally we get all of them back together. 1, 2, 5 and 10. So the key point with merge sorts is that it's very, very efficient because we're splitting up, because it's a divide and conquer. And we can also do this. And it's very efficient compared to bubble sort and insertion sort, because we're dividing each of the arrays. However, it's very inefficient for small lists like these. This one you could have easily used like insertion sort to put it back together. Or if the lists are nearly sorted, it's a downside because it would just require too much computation for no reason, basically. If it's nearly sorted, we could just use insertion sort to do it. And to summarize, bubble sort is the very least efficient algorithm. This is because as we have more and more data sets, we will need a lot more comparisons and swaps. This is why bubble sort is inefficient. However, insertion sort is more efficient compared to bubble sort because on average we would need less comparisons compared to bubble sort. However, the champion of all of them, all the two, is merge sort. Merge sort is much more efficient for larger lists especially. However, it's not the best algorithm for small lists and lists that are nearly sorted. So yeah, hopefully these make sense, and yeah, you can find the PDF of all the algorithms and explanation and everything on the website. Link in the description, and hopefully this video has been useful, and yeah, good luck for your GCSEs. I'll see you in the next one.